Hello, everyone. Today we're going to talk about lesson 2 on the combined gas law. The combined gas law is actually going to show us that the first 3 laws that we learned about, Boyle's law, Charles' law, Gay-Lussac's law, can be combined into a single formula. So I'd like to begin by just reviewing each of the previous 3 gas laws that we've learned. Okay, if we take a look at our first gas law, you'll remember that this is called Boyle's law that looked at the relationship between pressure and volume. We take a look at our second gas law that was called Charles's law, and Charles's law looked at the relationship between volume and temperature. And unlike Boyle's law, Charles's law was a direct relationship, meaning as temperature increased, volume also increased. Remember, with Boyle's law, as we increased one of the variables, let's say pressure, volume decreased. So that was known as an inverse relationship. Charles's law and, as you recall, Gay-Lussac's law are both direct relationships, meaning as we increase temperature, either volume, if we're talking about Charles, or pressure, if we're talking about Gay-Lussac's, both of those also increase. Now, combining all of those together, we get what is called the combined gas law. So here behind me, you can see a picture of the combined gas law. Notice that if we look at each individual part, in the green here, I have the Boyle's law relationship between pressure and volume. In the red, I have volume over temperature, which is what we saw with Charles's law. And then circled in blue, I have the relationship between pressure and temperature, which is better known as Gay-Lussac's law. Now, I'm going to clear out some of that mess so we can simplify this a little bit and just look at the combined gas law. One of the things that I mentioned in my previous lesson that students have the most difficulty with is solving for a variable. So keep in mind, when you're solving for a variable, 2 things must be true. The variable must be isolated, so by itself, no other variables should appear on the same side. And number 2, it has to be on the top of a fraction if there is a fraction. So in this case, we'll have to move our temperatures to the top in order to isolate them if we're solving for temperature. So let's go through real quick and see what each of those 6 equations would look like if we solve for them. So let's start off with pressure 1. So if we're solving for pressure 1, we want to move volume 1 and temperature 1 away. So we would get the equation pressure 1 is equal to, now keep in mind you can move variables diagonally across the equal sign. So pressure 1 is going to be equal to, T1 is going to go up here, V1 is going to go down here. So we'll have a final equation, pressure 2, volume 2 times temperature 1 divided by temperature 2 times volume 1. Now let's see what this would look like if we solved for volume 1. So volume 1 is here. It is already on top. So we're going to have volume 1 equals. We're going to move everything else away from volume 1. So pressure 1 is going to come down to the bottom. Temperature 1 is going to go up to the top. So we have pressure 2, volume 2, temperature 1, just like we had up here. But on the bottom this time, we have temperature 2 and now pressure 1. Let's try it again. This time, we need to solve for temperature 1. And this is a little more challenging for students because it's on the bottom of a fraction. So solving for temperature 1, the very first thing that we need to do is move it to the top. So now we have temperature 1 over here. Now, in order to isolate temperature 1, remember it's not here anymore. In order to isolate temperature 1, we have to move these other 3 variables away from it. So we're going to wind up with temperature 1 equals pressure 1, volume 1, and then temperature 2, that's going to go up there. So we'll have pressure 1, volume 1, temperature 2. Now, because temperature is sitting up here on the right, we have to get these 2, pressure and volume 2, away from it. So they're going to come down here on the lower left. We'll have pressure 2, and volume 2 on the bottom of our fraction. So we can also do this if we're solving for P2, V2, or T2. So I'll do that a little bit faster now on the right side. So if we're solving for pressure 2, I'm going to move everything else away from pressure 2. So temperature 2 goes up, volume 2 comes down. We wind up with pressure 1, volume 1, temperature 2, all over temperature 1 times volume 2. If we're solving for volume 2, it's going to be very similar. So we have volume 2 equals temperature 2 is going to go up, pressure 2 is going to come down. So we have pressure 1, volume 1, temperature 2 divided by temperature 1 times pressure 2. And finally, solving for temperature 2. So temperature 2 is currently on the bottom. So we need to move it diagonally to the top. So that gets rid of it down here. Now we need to move these other 3 variables away. So temperature 1 is going to go up to the bottom. Pressure 1 and volume 1 are going to slide down to the lower right side. So we have pressure 2, volume 2, temperature 1, all of that over pressure 1, volume 1. Hopefully rearranging for a variable is not a problem for you. But if it is, try some practice rearranging for each of these variables and see if you can get the answers that are behind you. Okay, since there's no new information to learn in terms of direct or inverse relationships, because we've talked about pressure, volume, and temperature extensively already, let's jump in and look at an example problem. Now, because we could have conflicting relationships between pressure, volume, and temperature, in some cases, we might not be able to easily predict whether our answer is correct based on the magnitude of the change. So, looking at example number 1, it tells us a gas has a volume of 800 milliliters. So this is going to be volume 1 at a temperature of negative 23 degrees Celsius. It's going to be our temperature 1. Of course, we're going to have to convert that into Kelvin. And our pressure 1, which is 300 torr. So the question then becomes, what would the volume of the gas be? So we're looking for the volume, and notice that it's asking for that volume in liters. So we have to do another conversion there at temperature 2 and pressure 2. So if you notice anything about this problem, the most important takeaway message is you want to get units to cross out. In order for them to cross out, they have to be in the same units. It's not going to be uncommon to be presented with a problem like this, where your variables are in different units, and before you can use them and before you can cancel out those units, you may have to convert them from one unit of pressure to another. Okay, let's take a look at this problem. So in this problem, we are told that our initial volume is 800 milliliters. However, the problem is asking us to find an answer in liters. So one of the easiest things that you can do to kind of save yourself some time later on is convert from milliliters to liters right now. So we have 1,000 milliliters in 1 liter. So that means our initial volume in liters would be 0.800 liters. So I just took 800 milliliters and divided it by 1,000. Next one, our temperature of negative 23 degrees Celsius. So you may recall me saying in our previous video multiple times that we're not able to use temperature in units of Celsius. So we have to add 273.15 in order to convert that to Kelvin. So negative 23 plus 273.15. Notice you do it exactly the same. It's irrelevant that it's negative. You just treat it as a normal number and put a negative sign in front of it. We wind up with a temperature in this case of 250.15 Kelvin. If you notice, our pressure is 300.0 torr. The second pressure that they give you later on in the problem is in ATM. So pressure 2 is 0.752 ATM. Now, you have a choice here. You can either convert your pressure in torr to ATM or convert your pressure in ATM to torr. It'll give you the same result, but they have to be in the same unit. So I'm going to convert my 300.0 torr into ATM. In our last video, there was a string of pressure values. Those are the values that you need to use in order to convert from one unit to another. So in this case, the conversion between ATM and torr is 760. So if I take this number and I divide it by 760 torr and multiply it by 1.00 ATM, I will effectively convert that unit from torr into ATM. 300 divided by 760 equals 0.39, and I'm going to round up to 3 decimal places. So we'll get 0.395 ATM. Just as a reminder, and so that you can write this down somewhere, 1 ATM equals 760 mmHg equals 760 torr, which equals 101.325 kPa. Now, in this case, we only are using the ATM and the torr, but you could potentially see problems with either mmHg or kPa as well. All right, looking at our last variable. So volume 2 is what we're looking for, and they give us temperature 2 as 227 degrees Celsius. So once again, we need to convert that into Kelvin. So we're going to add 273.15. This time, we're not going to be able to keep any of our decimal places because 227 didn't have any decimal places. So our answer is just going to be 500 point Kelvin. So no decimal places here. And now what I want to do is solve for my volume 2. So volume 2 is going to equal, here's volume 2 up here. It's going to equal P1, V1, T2 divided by T1 times P2. So now that we've isolated our variable, what we want to do is plug in our given values over here into our equation. So we're going to start off with pressure 1, which is 0.395 ATM. We're going to multiply that by our volume 1, which is 0.8000 liters. And we're going to multiply that by temperature 2, which is 500 point Kelvin. Now, after that part is done, we're going to do the bottom part here. So we have temperature 1, that's 250.15 Kelvin. In this case, we were able to keep both decimal places because we had 2 decimal places in negative 23. And our pressure 2, which in this case is 0.752 ATM. The one thing that I want to warn everyone about is when you type this into the calculator, you have to be careful. You have 2 different numbers that are on the bottom of your fraction. So either hit divided by twice, which is what I'll do, or use parentheses to enclose the bottom part, ensuring that you divide by both the 250.15 and the 0.752. Okay, you can watch as I type this into our calculator. So on top, I have 0.395. times 0.8. You can add in the zeros, but it's not going to do anything. Times 500 divided by 250.15, and then also divided by 0.752. If you don't hit divided by twice, you will get the wrong answer, or you can enclose it in parentheses. But if you don't do either one of those things, your calculator is going to divide by 250, and then it's not going to realize that you want to also divide by the 0.752, and it's going to end up multiplying by that, and you're going to get a really big answer up here. So in this case, we wind up with our volume 2 equal to, we're going to go with 3 significant figures here. So 0.840 liters. Let's take a look at one of our homework problems. So if you look at this homework problem, and this problem is already completed on your homework assignment, if I initially have a gas at a pressure of, so again, we're going to be using all 6 of our variables here. So we have P1, V1, T1, P2, V2, T2. So if I have all 6 of my variables, I'm going to read through the problem and fill these in as I find them. So if I initially have a gas at a pressure of 12.00 atm, a part's going to go here as P1, a volume of 23.0 liters, and a temperature of, notice they gave you the temperature in Kelvin already, so you don't have to go through the conversion part. So a temperature of 200.00 Kelvin. Then I raise the pressure to 14.0 atm and increase the temperature to 300.0 Kelvin. We're being asked to find volume 2 here. So looking at my equation, volume 2, I'm going to isolate that. So I have volume 2 equals P1, V1, T2. This comes up here. P2 is coming down. So we have T1, P2. I can now plug in my variables from the givens list into my equation. So I have V2 equals 12.00 atm times 23.0 liters times, in this case, temperature 2, which is 300.0 Kelvin. On the bottom, I'm going to divide by temperature 1, which is 200.0 Kelvin, and pressure 2, which is 14.0 atm. Typing all of this into my calculator, I have 12 times 23 times 300. I want to divide by 200 because that's on the bottom, but I also want to divide by 14, which is also on the bottom. So just to show you what that looks like when I pull it out here, notice I hit divided by, entered the 200, hit divided by again, entered the 14. So I wind up with an answer in this case of a volume, in fact, of, I have 3 significant figures based on the 23 liters, so 29.6 liters. Alrighty, that wraps it up for combined gas law. We're going to look at a few more gas laws in this unit. I hope everyone has a great week. If you have any questions, please stop by office hours or send me an email or Schoology message. Thanks, everyone.